Welcome to Hypermesh Radio's interface training. So this is a series of sessions which have been segregated chapter-wise. So where I'll be demoing each sections from the model building perspective for the Radio's interface. I'm Prashanth from Altair Engineering India office. So in session 1, the topics which will be covered is the mesh quality requirement for the explicit analysis using radios, and I'll be showcasing how to create and update the different kind of materials and how to create and update the properties. So this will be the agenda for the session 1. So this demo will be on the regular models. So I'll be moving to the tools in quite a while. So here the agenda is basically on the pre-processing part. So maybe like here and there I'll be touching a little bit on the radio solver, but largely it will be on the pre-processor, that is how to build a radios deck using Hypermesh. So that will be the main objective. To start with meshing quality requirement. So as a first thing, explicit requires a different kind of mesh quality, which I'll be explaining here. Having said that, you may be having a durability model already which have been meshed for, like if you see the durability model, you might have meshed certain region fine with the objective of capturing the stress data more detail. So basically, in the case of durability mesh, the entire model will not be of one global size. So don't get those models into explicit analysis because we have the different challenges here. So if you're if you're planning to start a explicit analysis, the first step is of course to think at the meshing level. Is that mesh is suitable for explicit analysis? So here I'm listing some guidelines. So the first one, like if the analysis is on a bigger model where the interest is on global behavior, like you're studying some global deformations, some global energies, some component interactions globally, basically something like a full vehicle impact. So this is the guideline for that. So first thing is to decide on the time step. So here sometimes your client may specify or your team leads may specify what is the time step. So once you decide on the time step, so we have a formula by which we can calculate what should be the least element edge length. Okay. So in the absence of any guideline, so if you don't have anything, the ideal start may be to assume 1 microsecond. Yeah, you may want to start with, you may want to assume that you want to run the simulation with a time step of 1 microsecond. So if you freeze that, and if you apply this formula for steel, you may end up with a minimum element size of 5.5 and for plastic, say 3 mm. So you have to make sure that when you mesh your model, none of the elements are below this value in element length. Okay, so maybe you can keep a global size of say 8 or 10 mm, and a minimum is 5.5. Otherwise, largely all the elements should be near to the global size. So as I was telling in the beginning, in explicit, you should not change the mesh densities very drastically. Okay, we want one uniform mesh in the model. Okay, so this is for the bigger models. So the use cases may be like, as I was telling, it may be for full vehicle impact, where the model I expect maybe from 0.3 to 1+ million, and you may be running it for few hundred milliseconds, say like 120, 150, 300 milliseconds, that kind of simulation. So why I'm putting this restriction? Because sometimes when you model is very big and your time step is very small, and if you're running it for a long events, then depending on the hardware availability, it becomes impractical to solve those problems. So before setting up any problem, you have to think of the hardware available with you, and how much runtime you can afford, and how much is maybe the requirement of this model. So depending on all these parameters, you have to arrive at one equation. And of course, the objective of the analysis is important. So if you have to meet that, you have to put that many number of elements of that particular size. This is for the bigger model, what I was talking about. But that is not always the case. Sometimes we want to study the feature level interaction. We may want to study some small snapshot, how they are behaving, or some small components, like if you take an example of a cell phone, there I cannot stick with a element size of 5 mm, as I was explaining in the previous slide. You have many small features, and in the event of drop test, of course you want to understand how the components are interacting. So when you are studying that type of component, so your guideline for meshing has to be different. So here I am giving some guidelines. So first you have to think like which are the important features which you have to capture. Now if I have a snapfit, and if that snapfit is sliding against a stopper, then for me that radius becomes very important. If I don't model that properly, then I may not get a right physics. So I have to capture that. So likewise, you may have many features like that. So first you have to identify which are those features which you have to capture, so that you can capture the physics properly. So once you do that, then here you have to decide what is the maximum size element that I can put to capture those features. So here it is not the minimum. So your thinking has to be always the bigger elements. Okay, maybe like say 0.2 or whatever. Okay, so here your thinking has to be like what should be the maximum size of element which you can put, but still capture the feature with a reasonable accuracy. So you have to think that what is the maximum size. So once you decide on that, you will mesh as per that. Okay, so depending on that mesh, you may arrive at a particular time step. Say you may arrive at a time step of 1 e power minus 8 seconds, something like that. You have to live with it. Okay, because here feature capturing is important. Otherwise, it will not give you the intended physics and what you want to study. So we try our max to have the bigger elements, so that even the feature is captured, you will get the physics right. With that, you will arrive at the time step, and you have to run the model with that time step. So in this case, the use cases may be like sometimes you are studying some small assembly which are having the total model size is like smaller than previous 0.1 to 0.3 like millielements. And here the one expectation is the events are quite fast. We expect the event to finish off in a span of say 50 milliseconds. Like if you take an example of mobile phone drop test, the event may finish as soon as maybe like 5 milliseconds. Okay, so since the event time is small, we can afford to use the elements of smaller time step. Okay, so in those cases, yeah, it is okay. But having said that, it is not always the case. Okay, there are one of the cases where the components are small, and you have to capture the feature. The model also becomes sometimes bigger, and event time also like it is, you have to run it for longer event times. There are cases like that, but if you're solving those type of cases, you have to keep in mind that these are the simulation which will be taking a much longer time. So either you have to use more number of cores so that you get your results faster. So you have to have all this thinking in the background so that you build a practical problem which is runnable. Otherwise, you will reach a stage where depending on the resource availability, you may not be able to run your problems. Though you mesh it, you set up the model, so you'll not be able to complete the run. So that's why, like, when you are deciding to do any explicit simulation, the first thing you have to put a well thought on which type of mesh I have to do, so that I can solve it comfortably and still have the reasonable good results. Okay, so this is on meshing quality. So from here we will directly switch to the tools, hypermesh, and there I'll be explaining how to set up the deck for radios. So for this demo, I'll be using the hypermesh version 2017. So I have launched the hypermesh. So when I launch the hypermesh, like it will give you the user profile options. So I'm going to radios here. When you drop down, you will see different like block 100 and so on. So these are different solver versions. Okay. So you have already chosen hypermesh as 2017 version, but you may have a requirement sometimes client specific that you are working in a solver version of some older versions. It is just the older versions of solvers. Okay. So now I'm just using now if I select this block 140, it means I'm using hypermesh 2017 and a radios version of 14. That's what I'm using it here. Okay. So now I have set the user profile. So let me pull a model. Okay. So here I have a meshed model. If you see here, this model has only components as of now, and I have kept some curves. I'll be also showing you how to create the curves, but I have kept some curves so that it will make my job easy while creating some of the entities. And there are some sets. That is why, because there are some connections which I have already created, so that it will save some of the time. But of course, I'll be showing you how to create different types of connections as well in the later sessions. But this model, as of now, it has just the components without any other things and with some basic connections. Apart from that, there is no other entities which are there in this model. So I have the activity of course, creating the materials and properties, which I'll be doing in this session. And later that I'll be creating the different types of connections which are required for this model. I'll be reading the loads and boundary conditions, and I'll be creating the contacts and different output requests. And finally, I'll be setting some control cards, and we'll be running the jobs. So those are all the things which will come in the later sessions. So in this session, as you have seen the agenda, so I'll be creating the materials and properties. And for the sake of easiness, I have also created some assemblies, so which will help me to quickly assign some of the entities. Now, if you see that I have made a separate assembly, okay, for all the frame structure and for some body, something like that. I have made some of the assemblies. So here, the idea is, of course, to demo the deck setup process for radios. So of course you may not find this vehicle as complete, so many entities or many assemblies may be missing in this one. But the idea is to showcase the features. So you may not find this vehicle as a complete vehicle. Okay. Okay. Fine. So now as a first step, I would start creating the properties. Okay, so for the people who have used HyperMesh in the previous version, now we are moving more and more to this entity browser and the part browser. So now we have many browsers here. So this is becoming more handy and more robust. So I'll be creating everything using these browsers. Okay, if you are a old user of Hypermesh, you might remember that we were using many of the options here to create those things. But moving on, so these are the new things and quite robust, quite easy. So I'll be doing the things here. Okay, now to first I will create the property. Okay, so I want to create the shell properties for the tubes. So let me name this as maybe tube frame. Okay, so this is the shell what I'm creating. So it is our recommendation to use the formulation as 24 and number of integration 0.5. I'll be using the thickness 2 mm for this, and this is again our recommendation to use this I thick and I plus. So these are our solver specific recommendation which we go in deep in our solver training. What are the importance of these parameters? Okay. So I just created a property for tube frame. Fine. So now I need few more properties. So let me create all those in one go, and later on I'll move to the other things. So here I have to create one more. So I will just say duplicate. Okay. So now this time this property is for the body. So all the other things will remain same. So only change is in thickness, which is 3 mm. Just do that. I need one more, which is wheel hub. The thickness of 7 mm. And again the tire, which is 4. And the leaf spring, which is 10. Yeah. So these are the different shell properties which I required, and I require one solid property also, which I'll be using for the seed foam. So let me create a solid property also. So I will say create again the property. So this time it is not shell. So by default when you open it will come as a shell, of course. And so if I had to use something different, I'll go down here. So this is our generic solid. So P14 solid. Yes. In solid also we have a different formulation, and if it was a hexa element, I would have used again iSolid 24 even for that, but this is a tet mesh, so I will stick to our default formulation, which is 0. Okay, so no other parameters here. That's it. So I created, okay, and just put a proper name. Okay, so I have created that. So just now I created like multiple shell properties, and I have created a one solid property. So I require few other properties also for the 1D element, which I will come to it at the later stage. Okay. So I'll go to the next step, and I'll create the materials. Again the same method. So I'm just right clicking and I'm going to this create, and I'll go to material. So the first simplest and the easiest material is a law 1 material, which is elastic. So here I'm using this for the tires, though the tires are made of rubber, and so the tires are the hyperelastic material. So I can use law 42, law 82, law 69, which are available in radios for hyperelastic. But here my study is not on the tires, so I can still use elastic. So it's just a tire, okay, elastic, and I will use density near to the hydroelastic material, Young's modulus, and some Poisson's ratio near to incompressibility. Fine. Okay, so I created one material. So this is the law one material, what I created for, which I'll be later using it for the tires. Then let me create the law 2 material, which is a Johnson-Cook. So Johnson-Cook is the basic non-linear material what you can use in radios, so it doesn't require any stress strain curve. It requires some of the basic plasticity parameters. Okay, so I'm going to law 2 here, which is Planck's jams, which is M2 or law 2. Okay. Okay. So here, of course, the regular. So this is steel. So I'm using the elastic parameters and that of steel, like or -9, 0.5. Yeah. At this stage, I want to make one important statement which I missed in the beginning. So for this entire session, the unit system what I'll be following is Newton, millimeter, tons, and seconds. So this is important because now you are seeing the material I'm inputting that unit system. So going further, whether it may be the load or time, so I'll be sticking to this unit system. Like any other solver, even the radios also will not understand any particular unit system. So it is your responsibility to maintain the consistent unit system. So unit system what I'm going to follow here. So let me repeat again. So it will be Newton, millimeter, tons, and seconds. Okay. So I'm using the Poisson's ratio of that much. Okay. Now here, so we have the A which is yield stress, and B is hardening parameter, and N is hardening exponent. So we have these entries which are required for Johnson-Cook material. But many a times, it is difficult to get these parameters from any of, whether from internet or through literature. For any particular material, it may not be straightforward to get the hardening parameter and hardening exponent. Okay, so in the absence of that, what you can do is we have other way of inputting the data. If we change I flag to 1, then it will ask you the yield stress, ultimate stress, and percentage elongation at UTS. Okay, so this is something which is commonly well known, which even in the like internet you will get the people talk in terms of percentage elongation for a particular material. So this is quite handy to enter the data. Okay. So otherwise, if you want to go with the parameters, yes, it is available. So now I'm going with that one, the old method. All are MPS here, hardening exponent, and sigma max, which is ultimate. Okay. So I have entered these values. Okay. So this I'll be using it for the string. Fine. Now let me create. Now we created law 1 and law 2. So I'll create one of the most widely used elastoplastic material, which is a piecewise elastoplastic material in radios, which is law 36. So I'll be creating that one. So you can see law 36 here, plus tab. Okay. At this stage, this here we have to enter the like density, Young's modulus, and Poisson ratio, regular elastic parameter. But it requires a stress strain curve. So this material requires a stress strain curve. So let me create that curve first and come back here. So I'm going to XY plot, curve editor. Okay, so I'm creating a new curve which I'll be using for tube material. Okay, and this is not the regular like full stress strain curve in this material. So this is a curve between true post yield stress versus true plastic strain. Okay, so here it starts with 0, and your first point will be the yield stress of the material. Okay, so I'm just going on with it. So I'm trying to create a curve. This is a good practice where we, after a ultimate value, we are just flattening the curve. Yeah, so this is your curve. Okay, now I'm back here. So I'm using the steel density. Sorry. Okay, and this material also supports strain rate input strain rate dependent multiple stress strain curve. Okay, so we have to specify like how many curves what we have. So depend, like for the same material, depending on the strain rate, you can have multiple strain rate dependent stress strain curve also. Okay, so here since I have only one curve, I'm just saying it is 1. Okay, so if I go here, see at this case, since it is only one curve, I have one tab opened here, and it is asking me with respect to this strain rate, and here it is just 1, so I don't have to put anything here. But assume that you have the curves at a strain rate of say like 0.1, 100, 1000, something like that. Then you can put the respective strain rates here, and the respective curves you can call it here. Okay, so now I'm calling the curve what I created. So I have called the curve, and I don't have multiple, so I'm just leaving it here. So otherwise you can specify that also. Okay, and the other data what you can specify here is, this is not mandatory. You can specify, of course, after what strain the element has to fail. Okay, this is a very crude, very basic way of representing the rupture. Rupture in a structural member is a combination of the strain, the material will be having the different strain in different failure strain in tension, different failure strain in compression, different failure strain in shear, and it will also get affected by the strain rate. So rupture is a complex physics. So here with this option we are not getting into that complexity. So here it just means in whichever the loading, if the strain crosses beyond this value, then the element should get deleted. As simple as that. Okay. So I'm taking some higher value, 25%. Okay. But of course, if you want to model those type of like complex failure models, even they are available in radios. You can use those advanced failure model also. Okay, so here I just created the plastab material, which I'll be using for tube. Okay, I will create one more law 36 for body. So this is again, it is law 36. Okay, and here I have already created, I have already kept the curve. So as initially I have showed you that in this model there are already some curves. Okay, so I just want to save some time in creating those curves. And now you already know that how to create the curve. So I'm just directly pulling that curve here. Okay, and for this also I will use EPS max as font. Okay, so I created 4 materials. Okay, so now for a seat foam I'll be using a foam material, viscoelastic material. So let me create that. So which is law 33, foam class. So here again density 1 equal minus 9. Okay, so here I require the loading curve. Okay, so I already have the loading curve in this model. Okay, so I'll be using that loading curve. So let me call that curve here. Okay, so this is the curve between yield stress versus volumetric strain. Okay, so I have created a curve, yield stress versus volumetric strain. So that curve I'm calling it here. Okay, so this is for foam. Okay, so I have created a set of properties and set of materials, and now it is to assign for the particular components. So now I'll be going as per the assemblies. So I will take this tube frame. So for this there is more than one method to assign the materials. So as I told, if you are the old user of HyperMesh, so we used to update the materials from here. Okay, or instead of getting into assembly, if it is one by like one of what, if we have the individual components, then you can go inside the component also and update the material and property here itself. Okay, you can do that. Or if it is multiple, as I'm doing it now. Okay, so I'm just going to select all these things. Okay, so then it will give me an option to update these things. So that is what I'm doing now, which is the quickest in this case. Okay, so I'm taking this tube structure. So property, it is already there here. So I'm picking it. Okay, and material also I have created for the tube. Okay, so for all these things it is assigned as of now. So now we have the interaction from the GUI to this browser also, which comes quite handy, because now this is while assigning, yeah, you're clear like what you are doing and what you have to assign, so you will do that. But later there will be always a requirement where you want to check what is assigned, or you want to pick some other part and you want to assign maybe a material of some other part. So these are some common application what we try to do. So in that case, we also have a utility where we will come to, maybe if I want to check at the component level, I have switched to component now, and I'm selecting maybe a particular part. So that part will be displayed what it is, which material and which property has been assigned. So like this. And if you are interested, of course, more in knowing the property or the material, I can always come to that. So now it's a material view. Okay, now in this case, of course, everything is assigned with as of now with the one material. So now I came to the material view, and I can select a particular component, so it will show me in which material has been assigned to this. Okay, so similar way you can check the property also. Okay, so all these things you can do using this property browser, using these browsers. Okay, so now I am at the assembly level. Okay, now I have assigned for the tube frame. So now in a similar way I'll isolate the body. So I will select everything. Okay, so I will assign the property and the material. Okay, so I'm done with that. So I will take the wheel hub, which is quite thick. So here again I will select them to get the component view of it, the part view of it. Okay, so this is the wheel hub, and for this one also I'm going with the material of body. Okay, so I'm done with it. So here okay, one step maybe previous to this, because now you have all the meshed things what you're seeing on the screen. So while meshing, these are standard practice to create, like we will create the components. Okay, so this will be our first step when we are starting the meshing of the parts. So we'll create a component. So by default, as you're seeing here, the component is coming in /part. Okay, so whenever the definition is /part, it will expect the property and material for it. Okay, and of course, if you have created any component for the purpose of rigid, then you have to declare that it's a rigid, so that it doesn't ask you for the part information. Okay, so in this case, everything has been done for the rigid. It has been called as a rigid, so everything is there. So you don't have to, like, you're already seeing it as a part. So otherwise, just keep in mind that when you create a particular component, you have to ensure that you have the part definition for that. Okay, fine. That is just offset from what we were doing. I just felt it's important information which I have to give you at this point. Okay, so now it's the tire. So I'll get into that. So I will use the tire property. And the material. Okay. So again, the leaf spring. Okay. So I'm taking that, this one part. Again, the leaf spring, property and material. Okay. So that is designed. Okay. So for this engine, actually engine is already there in the, it is also called in the body, but I have still made a separate assembly for this. If you check the engine, any of the component, you can see already it is assigned because we did it in the body, and inside the body I have also called the engine. But I have still made it as a separate assembly because there is a separate purpose for this, which I will tell you as we go further. Okay, so in the engine everything is assigned. If you see the property and material for all the components, it is already assigned. So I don't have to do anything here. Okay, now coming to the seat. Okay, so I have to assign the solid property, solid form, and I have to assign the material. Okay, So that is done. Fine. Okay. So as while creating the property, I mentioned like I created shell and solid properties, but there are some only elements which are there in this model. Okay. So for which I didn't create any property, so which I have to do it now. So as of now, I created for all the 2D and 3D mesh, I created both the property and material, and I have updated them. So that is complete. So now we are left with this one piece. Okay. Fine. So let me create the property for that, and then I'll come back and I will assign these things. Okay. So again, it is property. Okay. So we now first I will try to create a property for the bolt. So in radius, we model the like we represent the bolt using type 13 spring element. Okay. So I'm going with P13 spring beam element. Okay. So I'm going with this property. So this property requires mass and inertia for the purpose of time step. So I'm going with some minimum mass and inertia. Okay. And so what I'm making it here is, so I'm making it high stiff in all the direction, and this is a type 13 spring which follows local coordinate system. So since it is a beam type spring, the node 1 to node 2 is always x, okay, which is tension. But here I'm making everything high stiffness. So if you put this spring in the output request, you'll get to know how much axial or shear or bending load coming in these springs. You'll get to know that. And also we have an option like if you want to rupture the spring at a particular force or displacement or energy, you can specify those criteria by which you can also break the bolt at a particular load. Okay, so here I'm just making it as a high stiffness spring. For making it high stiff, I'm just selecting a value of 1 e power 5 Newton per millimeter. So that is the same value I'm using it for all the translation stiffness, shear Y and shear Z. And for rotation, I'm using a little bit higher, maybe 5 e power 5. So when we say high stiff, don't use any ambiguous value like e power 10 or something like that. Again, that may affect the time step of your run, because the spring then will have the least time step. Okay, so high stiff, yeah, maybe a reasonable value, which is quite high, what I'm using now. So you can use the same value if you want to model any high stiffness spring. Okay, so on all the rotations, I have used this value. Okay, just to make it as high stiff. Okay. So now, as I was telling, like there are different failure options. So we have the failure options here. By default, it is by displacement, and with the with force as a criteria and energy as a criteria. And we'll put the limiting values in these directions, in delta min and delta max. Okay, so in the tensile case, if I put this like this in the tensile direction and this will be in the compression. Okay, so I can specify these values. It can be, as I told, it can be either displacement or force or energy. So when the criteria is reached, that spring will get deleted. Okay. So here I'm not getting into those things. I'm just modeling one high stiffness spring, which I'll be using it for bolt. Okay, so that is created. Now next one, I want to model a suspension. For that, again, I will use this type 13 spring. Okay, but there is a difference. So you saw that I used a high stiffness spring to model the bolt. Okay, so I will use again the mass and inertia for this. Okay. Now suspension, of course, we expect the suspension uh, to act, of course, effectively in the along its axis, and it will have, of course, its own stiffness in the all other 6 directions also. But here my focus is basically on this axial direction of the spring. Okay, so suspension, as you know that now if I specify a stiffness here, it will become a linear stiffness. Okay, so suspension doesn't behave like that. Of course, it has a non-linear stiffness, and after certain displacement, it should lock. It should not further compress. So if you want to define that non-linear spring, then you have to use a function here. Okay, so you have to use a function. So let me create the function here on the fly. So I'm using the function. Okay, so this, let's call this as my suspension function. Okay, okay, so now I have to first complete this function so that I can come. Okay, sorry. So that I can come back and update the properties. Okay, so now I'm starting with 0 0, and let's say with displacement of 1, I will use some 100 newtons. So I'm creating some function. So again, the slope is not constant. With for 3, it is say 500, and for 10, it is 2000. 20, it is 5000. Okay, but now let's say I want to limit the displacement of the spring beyond this 20 mm. The spring will get, the suspension will get locked, and after that you don't have any displacement. So I will just use a high value here. So 20.1, and I will say something like 1 e power 5, very high value. Okay, so I just created a function here. Okay, so now I'll come back to the property. Okay, so you don't have to specify any stiffness in the linear direction. It will, the spring function will be followed with this function what you have defined. Okay, so it will work as per this. Of course, if you have a detailed property for the suspension in all the 6 directions, you can do the same thing. You can create the functions in all the other directions also. Otherwise, as a simplicity, again, I'm going with my high stiffness. Okay, so in the other directions, I'm going with high stiffness. So this particular property was you to show that how we can create the non-linear spring. Yeah, so just I created the non-linear spring, okay, so which I'll be using for suspension later. Now the last one, like you may want to create many joints, different types of joint you may want to create. So for joints, if the joint is very simple, like let's say you're creating some revolute joints, some cylindrical joints, some spherical joints, the very simple joints, and you're not worried about anything like a locking angle. See, some joints, they have to rotate a particular degree and they have to lock. So there are many fancy stuff what you can do with the joints. If you want to do some of the fancy stuff like the locking angle and the other stuff, so we have the quite advanced joints, which is a K joint, 2 element. You can use them. They are particular joint element. Otherwise, if you want to model the simple joints like this revolute and cylindrical, you can quite live with uh, one of the particular spring itself, which is our type 8 spring. Okay, it's a spring general. So again, this requires the mass, inertia. Okay, so by default, this spring works in global coordinate system. Okay, so you have to be careful while creating the spring. Now, depending on my model, say like where all, if I show you, like I have revolute joints, I have already a spring created here. Okay, so likewise I have many revolute joints, even I have a revolute joint in the wheel. So in this case, all the rotation are with respect to the y rotation. Okay, global y. So I have the rotation with respect to y. So how I'm creating this joint? So just let me complete. I am putting all the other stiffness as high stiffness. Okay, so all translation high stiffness. Okay, so even rotation X, again high stiffness. Yeah, now when it comes to rotation Y, so I am not giving any stiffness along rotation Y. Okay, so that makes it a revolute joint with respect to Y. So again I repeat, this type 8 follows global coordinate system by default, whereas type 13 follows local coordinate system by default. Okay, so now by making it like this, so Z, again high stiffness. Okay, so now I created a revolute joint in Y rotation. But this may not be the always the case. If given in a model, you may have the revolute joint oblique to any of the global directions. So then you have to create a local coordinate system. Okay, and then that local coordinate system you can call it here. Okay, so otherwise if it is aligned to global like this, yeah, it is quite simple. Otherwise also, if it is oblique to any global direction, then you can create a local skew and you can call the local skew. With respect to that, you can define the stiffness. Okay, so in my case, it is almost all the joints. Yeah, all the joints what I have in this model are revolute with respect to y rotation. That's why I have kept the y rotation stiffness as 0. Okay, now I have the properties. Okay, so just for the purpose of representation, I have left some of the elements uncreated. So let me create them and then assign the particular property. Okay, now my first job. Okay, so now my first job is to create maybe a suspension. Okay, so that I'll make it as my current collector. Okay, so now here I'll go to 1D and springs. So I'm selecting node 1. So if you observe, I'm not connecting the spring directly to the independent node of the rigid body. Okay, so there is a purpose for that. In radios, we should not connect any element to the master node of the rigid body. So that is one of the important things. So make sure that you always connect the elements to the dependent node of a rigid body. Okay, so that's why like I connected the spring element to. So I had one leg which have been left open for this purpose. So I have connected this spring to there. Okay. So just now I created one suspension. So similar way like the other things are already connected here. Okay. So I created a suspension. Now next I want to create one more, like one revolute joint. So that I will make it as my current collector. Okay. So even here, yeah. So for this revolute joint, so we are using the type 8 spring, and type 8 spring has to be of 0 length. Okay, so this is the other condition what you have to keep in mind. So the type 8 has to be always of 0 length. So now what I will do, either you can use the coincident picking and you can pick the nodes. The easier maybe first let me create it. I have left 2 open legs here. So I will create the spring. Okay, so I just created a revolute joint spring, and then I will make it 0. Okay, so I just make it 0. Okay, so they are not equalanced, so it is just a spring of 0 length. Okay, so between this leaf spring connecting member and the leaf spring, I made a revolute joint. Okay, now the last one I have to create a bolt, so I'll make that as my current collector. So again, bolt is also represented using the type 13 spring. So from the hypermesh representation, whether you create a type 8 spring or a type 4 spring or a type 13 spring, all the springs will look like this spring 2n, which just means that it is a spring with 2 nodes. So this spring 2n will not tell you whether it is a type 8 or type 13. For that you have to see the property of it. Okay. Now in that location I already have a bolt, so here I have to create a bolt. So again the procedure is same. So I will select 2 nodes. Yes, and I'll create a bolt. Okay. So just now we created one suspension element, one revolute joint, and a bolt, and all are having different properties as you have seen. Okay, now the element creation is over, but I have just created the property and have not updated it. Okay, so let me update them. So spring, of course, it doesn't require, any of the spring doesn't require material, it is only the property. So I'm calling, this is a bolt, so I'll call the bolt property, and this is a revolute joint, so I will call, I think, yeah, this is the one, I didn't properly named it, and this is the suspension. Okay, so and now I have the property for all the onlys also. Okay, so now we have the property and the material for all the entities in this model. So again, so the better way to check that one is, so go to utility table, and once you are done with all the assigning, come to this component table, and here you have to verify whether everything has the property and everything has the material. So I'm just checking that one. Okay, so of course spring should have or I can sort it so that it will make my life easy. I'll go to top. Okay, so this rigid body it should not have anything, so it doesn't have anything, and of course the springs have only property, no material, and all other entities have the property and the material. Okay, and all the shell has the thickness also. That is also one of the important thing to note. Okay, so everything has the thickness. Okay, so this table you can even make it editable. Okay, So here at this stage also, if you want to change maybe the property or the material, so there you have an option to change the property and material at this level also. Okay, fine. So now we have done this property and material. So one more material which is quite extensively used. It's not a material; it's a representation rather, which is rigid. Okay. So in a while doing maybe a simulation with complete vehicle, something like this. Now, if I take an engine, uh, engine, of course, we don't model the engine quite detailed. We only take the outer skin of the engine, and we just do a one wrap mesh. So in the mesh, so you have the shrink wrap mesh where you can just expose the surface, and you can just have an outer coating mesh. So we just mesh it like that, and we make that component as rigid. Okay. The outer mesh is required because in the event of impact, your engine is a very rigid member, so there is always a possibility that it will hit with your firewall or any other surroundings, uh, and it is having a huge mass, of course. So we want that representation of the engine, but we don't want to model that as a detailed engine because our study is not on the engine as such. Likewise, you have the transmission, and now let's say if you're doing a if you're doing maybe something like a drop test where you want to model a rigid floor. So for many of the application, we want to model some of the components as rigid. Okay. So when I say rigid, it means in the event of impact, there will not be any deformation on that. So of course, you will not see any stress and strain on that. But it will account for, you can make it to account for the mass and inertia, okay, which are quite important. So how to make that? Now in this simulation, like I have to make this engine as rigid. That's why I have kept it as a separate assembly. Okay, so for a moment, yeah, let me switch off this connector. Yes. Okay. Now this whole thing, I want to make it as rigid. Okay, so to make any one component or a collection of component as rigid, the procedure is, first of all, you should have the property and material on that one. So you should have, so in these components, if you see, as you saw earlier, all the components is assigned with one property and one material. Okay, so material can be elastic also, it doesn't matter, but it should have a material. And of course the property also, if you are matching the mass with the mass elements, then property also can be just maybe like 1 mm shell or some 0.1 mm shell, something like that. But essentially you should have property and material assigned to those components. Now what I will do is I will create a collector. Okay, so this is a this I'm creating it for rigid. So engine rigid. So here, as I told earlier, I have to make this as rigid so that it will not ask me for mass and property, those things. It's just a separate collector. Okay, now my collector is ready. I'm seeing engine rigid here. Now you have to come to only rigids here. This is a very important step. In radios, whether you're creating a rigid for a big cluster like this, or if you're creating a rigid for between one to one element, always you have to use the option multiple nodes and calculated nodes. Okay, so this should be your option while creating the rigids in radios. Because rigids, we also use it for connection purpose, which is my next topic, which I'll explain in the next section. But here our objective is to make this object as this entire engine as rigid. Okay. Now I'm just going with the selection of all the nodes. Okay, and I will say create. Okay, so it has just created one big rigid by connecting all these things. So this is how we make the rigid in radios. Now, if this entire rigid, if it has to be connected as some extra nodes to some other parts, then we just update this rigid, okay, and we add the other component nodes also. If you want this rigid object has to be connected to something, then we just extend the legs of the rigids to those components also. Okay, that is how we do. So this is quite an important thing, because people there is a mat 13 which says it is rigid, but it is entirely for a different purpose. So don't use that to create any rigid component. So if you want to make any component as rigid, so this is the procedure. Okay, so we have made the rigid. Now, if you want to add a mass and other things to this rigid, okay, so I can directly do the card edit. Okay, so I went with this approach, card edit, and I will add the mass to this spring. So maybe 200 kgs, 0.2 tons. That's it. Okay, so you can access the rigid body using this option also. Fine. Okay, so it is going to the same option to add the mass. Okay. So this completes this session where we created in the past nearly 1 hour. So we created different properties for shell, solid, and 1D elements. We created different materials: law 1, law 2, law 36, and law 33, which is foam. And we updated the model with these properties and materials. And finally, we created the mat rigid. Okay. So in the next section is quite an important section where we'll be creating different connections. So that will be the session 2. So we'll stop here. Thank you.